we start with a straightforward quiz, which pretty much covers everything we want to cover in this course about simultaneous equations. Okay. In precalculus, we go on to three equations and three unknowns. But we don't really need to do that here. It's very much the same. It's just a little longer. And if we get these methods down here, that should not be a big transition. So we start with the equation 5x minus 3y equals 2 and the equation 3x plus 7y equals 10. Now I number these equations. I put a 1 circle and a 2 circle. So the circled 1 stands for equation 1 and the circle 2 stands for equation 2. Then I document what I'm doing to the two equations. Everybody chose to eliminate x, and some people wanted to multiply the first equation by 3/5. Okay, that works, but it puts you into fractions, and you kind of want to, wherever possible, stick with whole numbers, integers. Okay, so we get by that. Instead of multiplying the first equation by 3/5 or negative 3/5, let's say, which would allow us to eliminate the 3x, we multiply the first equation by 3. So out to the left, I'll indicate 3 multiplied by circle 1 to indicate what I've done with the first equation. And that means I multiply every coefficient in the first equation by 1. Officially, I multiply the left side by 1 and the right side by 1. On the left side, I would use a distributive law. Well, anyhow, 3 times 5x is 15x. 3 times negative 3y is negative 9y. And 3 times 2 is 6. Okay, the second equation, we want to match up the x coordinates, no, the x coefficients. So we're going to multiply the second equation by negative 5. Negative, so we have a 15 and a negative 15, so we don't have to worry about subtracting negatives and stuff like that. Okay? So we get negative 15x because negative 5 times the 3x in equation 2. Okay? Negative 5 times the 3x is negative 15x. And negative 5 times the 7y is negative 35y. And then negative 5 times the 10 on the right-hand side is negative 50. So I think I'm seeing a place, no, maybe not. Yeah, I'm seeing a place. I think it's at negative 50. Yeah. Okay. But we don't want to make any identifying noises or some lawyer will sue us. Okay. In any case, now we add these. So I'm going to indicate that by just writing equation 1 plus equation 2, where equation 1 now refers to the first equation I wrote in the second step. Okay? I had equation 1 and equation 2, the original equations. I put a line under those, and then I wrote 3 times equation 1, negative 5 times equation 2, those two equations. Now I've got a line there. So when I talk about equation 1, I talk about the last equation 1, which is the 15x minus 9y equals 6, added to equation 2, which is the most recent equation 2, which is negative 15x minus 35y equals negative 50. And I get negative 44y equals negative 44. Then I divide both sides by negative 44. So I'm going to write to the left of this. I say solve y. And that's where where I divide both sides by the negative 44. And I get y equals 1. Then I substitute this into one of the first two equations. I'm actually going to flip a domino here. This is heads, this is tails. Okay, I got tails, which means I'm going to take the second equation. I'm going to plug, and it doesn't matter which equation I plug into. If I've done it right, I'm going to get the same result as in there. So I'm going to plug y in here, and I'm just drawing this looping arrow around here to indicate that the y equals 1 goes in for y. And of course, if you can't see the arrow, just to understand that in the second equation, second original equation, not one of the equations I got when I multiplied by numbers, back to the original equation, I'm substituting y equals 1 in the equation 3x plus 7y equals 10, which gives me the equation 3x plus 7 times 1 equals 10, which I then easily solve. 3x plus 7 equals 10. I add negative 7 to both sides. By adding the equation negative 7 equals negative 7, I get 3x plus 7 minus 7 equals 10 minus 7, so that 3x equals 3. And since I'm out of space, I'll sort of skip the step where I divide both sides by 3, which should be obvious to everybody. So I'm just going to say x equals 1. Well, that's the solution I get to the equation. Now, one thing that came up, one person made an error, did get that negative 50, and that ended up with ugly fractions. Okay, so I'm going to demonstrate what happens with ugly fractions here in a minute, but it's really simple. You just multiply both sides by the denominator. And you're going to end up with a solution that's still an ugly fraction, most likely, but it's just a fraction. Okay. Then you plug those fractions back in and find out that it didn't work. Okay. Or that it did, depending on what happens with your solution. Okay, so that's our solution by elimination. And I did elimination first because some people ran into a little problem with the elimination. Now let's graph these equations and see if this solution makes sense. Now we can verify that it makes sense because if x and y are both 1, then 5x is 1, negative 3y is negative 3. I said 5x is 1. 5x is 5, and negative 3y is negative 3, and 5 minus negative 3 equals 2. In other words, I've substituted 1, 1 into the equation 5x minus 3y equals 2 and seen that it's true. In that, I substituted 1, 1 into the second equation, 3x plus 7y equals 10. Well, x and y are both 1, so 3x is 3, 7y is 7. And when I add those, I get 10, which is what I'm supposed to get. So I've verified the solution. Now, graphical solutions are important. So let's go ahead and graph the solution. Okay. The first equation, 5x minus 3y equals 2. I'm going to graph this by intercepts. The x-intercept occurs when y equals 0. If y equals 0, then 3y equals 0. And we get x equals 2/5. The equation becomes 5x minus 3 times 0 equals 2. 3 times 0 is just 0, so we get 5x equals 2. Then divide both sides, we get x equals 2/5. The y-intercept, when x equals 0. And again, I urge you to remind yourself that the x-intercept occurs when y equals 0, the y-intercept occurs when x equals 0, and always write that out if in very abbreviated form if you wish. But you want to keep reminding yourself because people, when we get into other types of functions, forget about it. Okay? There's a strong tendency to forget about it. So we want to keep reminding ourselves of the things that are important. So if x is going to be equal 0, then we're going to have 5x minus 3y equals 2 becomes 5 times 0 minus 3y equals 2. And we get negative 3y equals 2, y equals negative 2/3. I don't want to put these points on the graph until I see what the intercepts of the other equation are, so then I know how to scale my graph. Okay, so I've got 3x plus 7y equals 10. X-intercept occurs when y equals 0. I'm writing that out. I didn't write the words. I wrote x dash int colon y equals 0. It only takes about 3 seconds to write that out, and it's worth doing. So we're going to have then just 3x equals 10. Now I have skipped a step there. I didn't write 3x plus 7 times 0 equals 10 because I know that 7 times 0 is 0. So the left-hand side will just be 3x. And then we get x equals 10/3. Now notice that this fraction is greater than 1. It's 3 1/3. The fractions we got for the first equation are both, well, they're 2/5 and negative 2/3. They're less than 1. So this 3 1/3 is several times bigger than the 2/5 we get for the x-intercept here. That's going to tell us something about what kind of a scale we want to put on the graph. Okay. Then the y-intercept occurs when x equals 0. When x is 0, 3x is 0, so we're going to get 7y equals 10. Y equals 10/7, which is 1 3/7. Well, the biggest x coordinate we have is 3 1/3. So I'm going to draw a line, vertical line, out close to the arrow on my x-axis and label that x equals 4. Now the biggest y-intercept we have is 1 3/7. So I'm going to do one of two things, and I'm going to do the weird thing. I'm going to distort the graph a little bit, and I'm going to draw my y equals 2 line, just a dotted line for y equals 2. So that goes through the y-axis up close to the arrow on the y-axis. Okay. And the way I've drawn my coordinate axes, that means 2 units of y is about as big as 4 units of x. So this graph is not going to be to a uniform scale. Everything on the x-axis is going to be consistent with everything else on the x-axis, and everything on the y-axis will be consistent with everything on the y-axis, okay? But the numbers on the x-axis are going to be closer together in a sense than the numbers on the y-axis. Okay, so I've got my y equals 2 line, and halfway between there and the x-axis, I draw the y equals 1 line. So now I've got a picture of how big y equals 1 is, and my y-intercepts are 1 3/7 and negative 2/3. Okay. Now, I've got my y equals 1 line, so I'm going to sketch a y equals negative 1 line so that the y equals 2, y equals 1, y equals 0, which is the x-axis, and y equals negative 1 lines are all pretty equally spaced. and then I can subdivide within those lines. Okay, now my x's, well, I've got the line for x equals 4, so just to get a scale, I divide between x equals 4 and the y-axis, where x equals 0. I draw a line where x equals 2. And then halfway between the x equals 2 line and the y-axis is my x equals 1 vertical line. And halfway between the x equals 2 and x equals 4, we're going to have x equals 3. So now we can pretty accurately locate our points. Okay? Now, for the first equation, the x-intercept is 2/5. I could divide the interval from x equals 0 to x equals 1 into 5 parts with 4 little. Yeah, I didn't do a good job of that. But there it is. And I see that 2/5 goes a little less than halfway between x equals 0 and x equals 1. So I'm going to draw a point about here. I'm going to put a little mark on the x-axis at that point. And I think I've got a fairly close, maybe should be just a tad bit to the left, a millimeter to the left, but we'll go with it right there because this is just approximate. Okay. And then we have y-intercept at y equals negative 2/3. Well, that means I can take the interval between y equals negative 1 and y equals 1, try to divide it into 3 equal parts. And on the second part below the x-axis, I draw my y-intercept. Now, this is a little bit tenuous because I really don't think I've located those 2 points exactly where they ought to be. However, if I sketch a line, well, there it is. I think I did a fairly good job of hitting the points. Now I know where the line ought to hit certain places, and it doesn't, but that's inevitable with a sketch, okay? With a hand sketch. Okay, now my x equals 3 1/3. For my second equation, the x-intercept is 3 1/3. So I come out to x equals 3, and then divide the interval from 3 to 4 into 3 equal parts, and make a mark at the three and a third point. If I've got 2 marks in between to divide this interval from x equals 3 to x equals 4 into 3 parts, the first one to the right of the x equals 3 will be 3 1/3. And I do that on the x-axis because that's the x-intercept. The y-intercept is 1 3/7. So we come out to the y equals 1. Now, I could divide the interval between y equals 1 and y equals 2 into 7 equal parts. That's kind of hard to do, to make them equal. So I'm just going to say, well, I'm going to make a line halfway between, and that's at y equals 1.5. And 3/7 is just a little less than a half. Okay. A half of 7 is 3.5. So 3.5/7 would be 3.5. What would be a half anyhow? I'm going to draw a mark where I kind of think 1 3/7 ought to be just slightly below 1.5. Then I'm going to draw a line between the x-intercept and the y-intercept. It's a little high. And I'm going to estimate the coordinates of the point where the line crosses. Well, on my graph, that line crosses pretty well on what I constructed as the y equals 1 line. So I'm going to sketch a vertical line through the point, and the horizontal line through the point is going to agree with the y equals 1. Vertical line through the point looks like it's about at x equals 1.3. X equals 1.3 with a well-constructed question mark there. We're not sure of that. So we estimate solution. Now I estimated by decimal 1.3. I'm going to write that as 1 3/10. Then y is 1. Now we want to see how accurate that solution is. Of course, that's pretty close to the solution that we know we should be getting, 1, 1, but we don't fudge it. And usually we're going to do a sketch before we do the actual solution. So we won't be able to fudge it. One second while I rearrange the boards here. Okay. Now we want to check our solution. Check the estimated solution. One 3/10. Actually, I'm going to, just to illustrate, I would estimate 1.3, but I'm going to call that 1 3/11, which is about as close as 1 3/10. So I'm going to change my estimate of x, and we wouldn't estimate 1 3/11. We'd probably estimate it with a decimal. Illustrate what happens when you get a fraction in a solution and you're trying to check. Okay? Because this is real important and people tend to forget about this. 1 3/11, 1. We're going to substitute this into our original equation 1, not one of the equations we got when we started multiplying things and so forth. Our original equation 1, you recall, is 5x minus 3y equals 2. So what we get is 5 times 1 3/11, which I'm going to write as 14/11 because we don't want to do arithmetic with mixed numbers. Okay? And we know that 1 3/11 is 14/11. 1 is 11/11, and another 3/11 makes 14/11. Okay? And then it's minus 3 times 1 equals 2. I'll put a question mark on that. Well, we really don't want to deal with denominators, so I multiply both sides by 11. And I get 11 times 5 times 14/11 minus 11 times 3 times 1 equals 11 times 2. Multiplying 5 by 14/11 gives us 70/11. Multiplying that by 11 gives us 70. Well, I'm going to write that out. Okay, it's 11 times 70/11. Then 11 times 3 times 1 is 33. 11 times 2 is 22. There's something wrong here. Okay, well, I get what I get. And I'm going to get 37 equals 22 out of this. That's okay. 11 times 70 over 11. If I multiply the 11 by the 70, that'll be the numerator of this fraction, and the denominator will still be 11. 11 is a factor of the denominator and a factor of the numerator, so I can divide it out. I get 70 minus 33 equals 22. 37 equals 22. Now, that's not great. It's not all that close, but let's see what we get from the second equation. Now, without going through all the detail, 3x plus 7y equals 10. If we plug in 1 3/11 and 1, we're going to get 42/11 plus 7 times 1 equals 10. Multiplying everything through by 11, we get 42 plus 77 equals 110. And 42 and 77, I believe, is 119 equals 110. That's fairly close. I'm not going to try to interpret that solution any more closely. Simply say if I went back then and divided both sides by 11, I'd have 37/11 equals 22/11 for the first equation, which isn't off. It's only off by 17/11, which is more than we'd like. And the second equation will be off by even less, but don't need to even think too hard about what I said. Main reason was to illustrate how much simpler equations become if you multiply through by denominators. I want to keep emphasizing that. Okay, so if we hadn't done a check on our graphical solution, and then if we had done our solution by elimination, we would find that they're plausibly close. Solution should be 1, 1, xy equals 1, 1. And the solution we got graphically was about 1 3/11, 1, which is pretty darn close. Okay. So we tend to believe our solution by elimination. We tend to think it was confirmed by the graph. And also then we can check our solution by elimination by plugging our solutions back into both equations and saying that they both give identities. Now, I also ask for solution by substitution, and that takes a little bit of work because these equations are not naturally set up for substitution. Still, when you get into substitution with nonlinear equations, which you encountered in a recent homework assignment, you need to know what to do. Okay, so again, we have our system. And we're going to solve it by substitution. So we write out our system, 5x minus 3y equals 2, 3x plus 7y equals 10. And then we solve the first equation for y. Yeah, we could solve it for x or we could solve it for y. And since we're used to like y equals mx plus b, a lot of times by default we solve for y. But it really makes no difference in this case. But we're going to solve it for y. So we've got 5x minus 3y equals 2. We're going to subtract 5x equals 5x. We're going to add the equation negative 5x equals negative 5x to both sides of the original equation. Now, if you're seeing this, a lot of times you're just taught to write a negative 5x under the 5x, and then a negative 5x somewhere on the other side. And you're not necessarily taught to write an equal sign. Okay? I respectfully disagree. You're adding an equation to an equation. And that's exactly what we do when we do elimination. So I've been telling you all along, you add equations to equations. You don't just magically put two things underneath the original equation and expect to understand what it is you've done. Although you probably do. So I've been kind of emphasizing that. So the idea of adding equations to equations won't be as weird to you when you first see it, when you study elimination. Well, I'm not trying to make excuses for some dumb thing I did, just trying to emphasize the way I want you to think about this, okay? Then I write out the equation 5x minus 3y minus 5x equals 2 minus 5x. And that's exactly what I get when I add 5x minus 3y to the left-hand side, 5x minus 3y to the left-hand side of negative 5x equals negative 5x. Okay, I get 5x minus 3y minus 5x. On the right-hand side, it's 2 and minus 5x. I write 2 minus 5x. Then the 5x's, well, 5x minus 5x is 0. So on the left-hand side, I'm left with just negative 3y. On the right-hand side, I had 2 minus 5x because that's kind of the order in which the addition was done. But I'm going to write it as minus 5x plus 2, which is a more familiar, it's more grammatical. Okay. Then I divide both sides by negative 3 because I'm trying to solve for y, and I'll have negative 3y equals. Then I've got negative 5x plus 2 over 3. And that gives me y equals, I'll write it as negative 5/3 x plus 2/3. The 3 in the denominator, when the numerator is negative 5x plus 2, the division by 3 distributes through the addition, okay? Division is nothing but multiplication by a reciprocal. Multiplication distributes, division would darn well better distribute, okay? Okay, well, we've got this solution for y. Now, how do we get a solution to our system of equations? Well, we plug this expression for y I'll do it into the second equation for contrast. Maybe I should have done it into the first. But this will be okay. So out of that, I get the equation 3x plus 7y, which is 7 then times the quantity, minus 5/3 x plus 2/3 equals 10. Well, I'm going to go ahead and distribute the multiplication by 7. That's going to give me 3x minus 35/3 x, 7 times negative 5/3 x, and then plus 7 times 2/3, which is going to be 14/3. And then I've got to remember to multiply 10 by 7. The right-hand side has to also be multiplied by 7. No, I'm not multiplying by 7. I'm thinking ahead, but I'm going to multiply by the denominator. Forgive that little mental slip. Okay, so the right-hand side is still 10. Now I'm going to multiply both sides by 3 to clear out these denominators because they're irritating me. Okay? The reason you want to do that, even if you're good with fractions, is you're less likely to make a mistake if you're dealing with whole numbers and integers than if you're dealing with fractions. So even if you're adept. Now I'm writing out the whole mess. I'm writing out 3 times the quantity 3x minus 35/3 x plus 14/3. And now I've got to remember to multiply my right-hand side by 3, and that'll be 3 times 10. Now, I'm at the bottom of the board. I've got to come up. I'm going to rewrite my add order. Okay. When I multiply by 3 by the quantity 3x minus 35/3 x plus 14/3, I get 9x. And then 3 times negative 35/3 x. The 3 will end up as a factor of the numerator. 3 is the denominator, so that 3 in the denominator divides the factor 3 in the numerator. It leaves me minus 35x. I keep saying all that because people don't understand the rules of calculation. People typically don't understand the rules of calculation very easily, of cancellation, did I say calculation? In every case, we're dividing a factor of the denominator, which is 3 in this case, into a factor of the numerator, which will be 3 when we multiply 3 by the 35/3. Okay? And then same thing with the 14/3. 3 will be the denominator. A 3, you're going to have 3 times 14 in the numerator, so you can get rid of the 3's. And our left-hand side becomes 9x minus 35x plus 14. And the right-hand side is 3 times 10, which is 30. This equation simply has to look or feel better to you than the equation with all the fractions in it. And if it doesn't, maybe you're just really good with fractions, and yeah, okay, you have my respect and admiration. I'm good with them, but I still prefer to go with the integers. Okay? Less error prone. 9x minus 35x is negative 26x plus 14 equals 30. Now, I happen to know that the solution should be x equals 1. And what I've done here doesn't give me x equals 1. When I subtract 14 from both sides, then I end up with negative 26x equals 16. That's not even close. So now I've got to go back and debug whatever it is I've done wrong. Let me take a quick look at it and see if I can figure it out. Don't see anything wrong there. Don't see anything wrong there. Goes all the way back to when I divided by negative 3. I had in solving the first equation for y, I subtracted 5x from both sides, got 5y minus 3x minus 5x equals 2 minus 5x. I divided both sides of that equation by -3, but I didn't. I divided the left-hand side by -3, and I didn't have a negative on the right-hand side. So everything after that was wrong. So my signs on the right-hand side have to change. And unfortunately, I'm not going to be able to take time to explain everything that I'm doing here. But if you can see what I'm doing. I'm just changing everything that's involved with that -5x. When I divide by -3, I get plus 5/3 x. And then when I divide the +2 by -3, I get -2/3. So I'm having to change the sign on the 5/3 and everything I get from the 5/3. So my -35/3 should be positive. My +14/3 should be negative. And if you can't see this, you can go back. You followed the steps so far and correct what I've done. It'd be a good exercise. If you understand it, you can go ahead and apply it. So when I got that up to my equation, 9x minus 35x plus 14 equals 30, the -35x came from dividing the -5x by 3. I should have divided it by -3, so that changes the sign on the 35. And the plus 14 came from dividing the -3 into 2. When the right-hand side was -5x plus 2 over 3, it should have been -5x plus 2 over -3, and that would have given me a -14 here. And that gives me something familiar. Now my equation should read 9x plus 35x minus 14 equals 30. 9x and 35x makes 44x. So I have 44x minus 13 equals 30. I add 14 to both sides. It's going to do 3 dots on the board since I've wasted a little time here. But it's clear that I add 14 to both sides. I'm going to end up with 44x equals 14 equals 44. And then it's clear that x equals 1. At this point, we would substitute x equals 1 into either of the first two equations. And just as happened before when we got x equals 1 from elimination, we're going to get y equals 1. So I'm just going to write here substitute x equals 1 into either original equation. Find that y equals 1. Then plug x equals 1 and y equals 1 into the other original equation. And what you get is an identity. You get this, whatever number is on the left-hand side equals whatever, equals the same thing on the right-hand side. Left-hand side will equal the right-hand side. That's what we mean by an identity. And that verifies the solution. one thing you can see from this is that it's a little more complicated to use substitution for two linear equations than it is to use elimination. Elimination as we can now see, got us down to y equals 1 in just a couple of steps that never involve fractions, although solutions often will involve fractions. And then it was easy to substitute that into one of the original equations and find that x equals 1. And we got the whole solution more quickly than we would have gotten this solution even if I hadn't had a mistake. Okay? So that's one thing you want to take away. The other thing is that board in a precarious position for a minute, is what happens when you plug in fractions. Okay? You want to multiply both sides by common denominators. Now that pretty well covers everything that you're going to need to be able to do up to spring break. And there's no additional assignment over spring break. There's one assignment due in a couple of days. That's on elimination, which ought to give you time to refresh yourself a little bit over spring break. But, you know, that's the good news. The bad news is there will be a midterm the week you come back. It'll be in the testing center. It'll be there all week. If you want to take it before that, just let me know. And I'll send out a sample. What I have handed out in class is, make sure this is it. The same thing that was posted last week, I think, on your website, where there's an infinite number of problems, essentially. More problems than anybody in their right mind will do, okay? And most of these problems have solutions. There are a couple of errors in the problems. For example, sometimes the problem is incomplete. It says, you take the following expression and do this, and there's no following expression. Little glitch in the program, which I just need to rerun so I can post it correctly. And what I've given here is the problems numbered 101 through 200. 200, okay? Well, 200 shouldn't even be there. And also, but everything else is legitimate for the test, except for the stuff where the problems numbered 175 to 177, say like 175 exponents 0, 0, okay? 177 exponents 0, 2. If you know how to do the exponents, fine. That's going to be the first thing we do when we come back. You don't need that for the exam or for the midterm. Pretty much everything else on here is legitimate for the midterm. So I would recommend that you kind of use this as a study guide. This is one version, okay? Covers 4 pages front and back. And there aren't really 100 problems there because of the numbering system I use. There are a lot of gaps in the numbering system. I think there are probably close to 100 problems. And it wouldn't be a bad idea to work through them, especially the ones you're not sure that you could immediately work. Might not have time to work through all of them, but you at least want to review everything. And this will give you a good idea of what needs to be reviewed. I also don't guarantee that all the solutions are accurate. I've checked them pretty carefully. I think most of them are. If you get a solution you're pretty sure of and it doesn't agree, I'd appreciate it if you just email me and say, hey, that solution didn't match what I got. Did I do it right? Okay, that allows me to do two things. First of all, tell you, well, yeah, that was the right solution. You didn't do it right. Tell me a little bit about what you did, and I can maybe help you. Okay. Uh, and the other thing is it allows me to go into my program and correct source file. So when I regenerate it next round, the solution will correct. Okay. So thank you and have a great break.